All right, all you chemistry people. Today we're going to review a little bit accuracy and precision, and then introduce you to something called percent error, which is pretty helpful when we look at the next lab we're doing. So just a few things to talk about and review. And as we look at this here, um, idea number one up here, it says measurements 3.25 centimeters are different than other numbers. We got pi there from your math class there. The big thing is when we take a measurement or when we have a measurement such as 3.25, we're getting that from some sort of instrument or some sort of ruler or some graduated cylinder. So automatically we have built-in uncertainty. No measurement is ever exact. And also on top of that, as you can see, pi here has no units, whereas a measurement does have unit. That's pretty important. Because of this uncertainty, we have to be able to communicate it, but all be playing by the same rules too, so that we're able to do science together. So the first thing we'll talk about here in review is accuracy is how close we are to the true or accepted value, the actual. So think of accepted, actual, accuracy, all a bunch of A's there. So then precision, on the other hand, is going to be how close a measurement is to other measurements. So these are both very important things in science, but we want to be accurate and precise. If we look down here, and you've done this before, but just to kind of review a little bit here, if we look at this one right here, this target, the question is, are we accurate? Well, the actual, the accepted, the real target we're looking for is bullseye. So we did not hit that bullseye. So no, we are not accurate. However, precision, they're very close to each other. So we would say that precision-wise, this is extremely precise in the data set because you got all of these arrows hitting in the same spot. Now, look at this. Accuracy, definitely hit the bullseye. That's the actual target. This is not the actual target. This is the actual target. And then, of course, this is precise too because we got measurements close to each other, or targets close to each other. Over here, if we look at this, we are not very accurate. Even though we got one shot in the bullseye, we're not considering this to be accurate, and we're definitely not considering this to be precise because of all the craziness here. Hopefully, nothing new right there. Now, finding averages and seeing how precise we are, because there are going to be times you're going to do labs and you're going to get either a bunch of your own measurements, or there's going to be 7 to 12 teams, groups around the room, and we'll compare our data and see how close they are. Hopefully, we'll see that they're very close to each other. But we'll look at these numbers right here, and we'll say, okay, so let's pretend for a second that we have several groups, and we're getting all these numbers here. We kind of want to see, as we measure the density of aluminum, we kind of want to see what's going on. How precise are we? So if we were to take all these numbers and find the average, so we would add them all up on our calculator and then divide by 7. That's how we find the average, of course. So if we'd add these up, punch this into our calculator, then divide by 7, we would get an answer of 2.7. Now, as you look at 2.7, you're probably thinking, well, that's not crazy because several of these measurements up here are pretty close to 2.7. Now, something we'll want to do then is we're going to want to also consider a range or a plus or minus that kind of gives us that. So we'd want to go with our highest value and our smallest value. So it looks like our highest value would be 2.8 right there. And then our lowest value would be 2.6. So what it says here, subtract the highest value from the lowest value. I go ahead and do that by taking, again, 2.8, 2.6, and I get an answer of 0.2. Then it says, go ahead and take that number and divide it by 2. It says it right here. And that is going to give me 0.1. So now I have the precision of the measurement. And that precision of the measurement is 2.7. That's where I get this from. I get 2.7. That's my original number. And then I'm going to plus or minus, kind of like a range, right there. All right. So this is sort of the same. This is seeing how similar we are in our measurements around the room, and if we're precise. In other words, um, are we confident that everybody in the room is getting a measurement that is consistent and able to be trusted? Here's more data, and for the sake of time, we would do the same thing with that. So I'll give you a chance to do the calculations there and then put your answer into the play pause it. So you'll do the same thing down here. Go ahead and give that a try. All right, nice job. Let's move on to another important thing, and this is doing the percent error. This is something we're going to do all year long in chemistry. And the big thing is we're calculating the percent error. The way we're going to do it is we're going to go, it says actual value and measured. Now, sometime we're going to call this theoretical. Okay, theoretical means in theory. I won't spell it all out there, kind of abbreviate it. And then measured sometimes is going to be called observed. Okay, sometimes we'll use theoretical and observed, but this one says measured and actual. So pretty much the same idea here, different words. Working in the laboratory, a student finds a density. So we got some words, we got some numbers here, 2.8, and then we have 2.85, excuse me, and we have 2.69. So if we look at this here right away, we're going to try to decide which one is the actual, which one is this one, and which one's the measure. Okay, so since this, it actually says the accepted value is going to be this one, and then since the student found the density, this is definitely going to be our measured. Okay, so now something that we didn't put up here, and that is that you're always doing the absolute value. So you're never going to have a negative number. It's simply the absolute difference between actual and measured. So I'm going to put 2.699. This is my accepted or my actual, and I'm going to subtract from that 2.85. And that is the absolute value from that. Subtract those two right there. And then I'm going to divide it by the actual or the accepted, which is 2.699. So what would that answer be? Well, after I multiply it by 100, so after I find the difference, multiply it by 100, and then my answer would be a percent, which is basically telling me how much air I have, 5.59, 5.59%, just like that. Okay, that's how we do that. Let's try another one. So we're down here and we're looking and we're saying, okay, we have a student experimentally. Okay, so he's measuring or she's measuring 4.29. And then we look it up, and the actual value is 4.18. So again, I'm going to put 4.18 as the first thing listed. I'm looking right here, actual, minus the measured, and the measured is 4.29. 9. I don't care that this is going to be a negative number because it's an absolute value. And then I'm going to divide it by the actual, which again is 4.18 here. And then I have to multiply this out, okay? So again, as you're working at home here, first thing you're going to do is you're going to take these two numbers, subtract them, get rid of the negative sign, divide by this number, and multiply it by 100 to get an answer. And you should have got 2.63%. That's how you do that. Let's do one more. Again, a student takes an object with an accepted, okay, an accepted. We know that it goes actual minus measured or observed divided by actual. We know that from before. So this is the accepted mass. So that's going to go here and here. And then he records or he measures this one. So that's going to go right here, 196.5. This doesn't matter. That's an absolute value. But it does matter that I multiply it by 100. And check yourself. Go ahead and calculate that. Again, how are we doing this? We're taking this 200 minus 196.5. Then we're going to divide it by 200. Then we're going to multiply it by 100. And that is going to give us an answer of 1.75 and percent is the label. That's a pretty good one. That's the best one we had so far because it's actually the lowest. And that kind of makes sense. It's pretty close to the other ones. Okay. So, and I'm going to go ahead and kind of skip number 4 just because I don't think we really need this one as much as the other one. So what you're going to want to do is skip that. But remember, this is how we find percent error. And hopefully this helps you out a lot as we go forward.